Time is X minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
And welcome to the Big Bounce, the Festival of Physics 2020. We're here live from the East End of Glasgow, just outside the legendary Barrowlands Ballroom. We've had a fantastic event so far today, Fast Physics, but now we are moving on. We're moving on to a subject that's going to, I think, absorb a lot of our attention in the next few years. We need energy. We need new sources of it. We are looking everywhere we possibly can. Our next speaker is looking into a word that we've heard a lot of, but quite a lot of us don't understand really what it means: fusion. What exactly is that? And our next speaker will be taking us on to that. We'll also be doing a Q&A about this, so there's a little screen at the side there at the YouTube. Please get your questions in so that we can put them to our speaker after her presentation. Also, there's going to be another event, a sort of workshop with our speaker after at 5 o'clock. You need to sign on for that as a Zoom. If you go to the bottom of your screen, you can sign up for that smaller, intimate event where you can get even more information about this riveting topic as we move into a new world where we need to find new sources of power. It's fusion. And Dr. Melanie Windridge is going to explain to us fusion, the power of the sun.
Hello, I'm Dr. Melanie Windridge. It's a pleasure to be here today to talk to you about fusion energy. Fusion is a possible new energy source, one that is clean, green, safe, and abundant. It is the reaction that powers the sun and the stars, and it's been enticing scientists since they first figured out what was causing the sun to shine. If we could do fusion, it would change the energy landscape, perhaps even change the world. I think that this next decade is going to be really exciting for fusion energy, and I want to tell you why. So, what is fusion? Fusion is the reaction happening in the sun and the stars. It's the way the sun makes energy. Hydrogen fuses to make helium and releases huge amounts of energy. Imagine if we could have our own miniature stars producing fusion energy here on Earth. If we could do this, we could produce abundant energy with no greenhouse gases. We wouldn't have to worry about running out of fuels because the types of hydrogen we need come from readily available sources like seawater, and the reaction produces a lot of energy. Just 1 kilogram of fusion fuel produces as much energy as hundreds of truckloads of coal. Half a bathful of water and the lithium in a laptop battery would be enough to cover your lifetime energy needs. Fusion would complement renewables to provide baseload electricity to keep the lights on during peaks and troughs. Fusion could provide industrial heat to clean up dirty industries. Fusion could generate hydrogen as a replacement for natural gas. Fusion could provide clean electricity for transport, or even technologies to scrub CO2 out of the atmosphere. Fusion would power economic development around the world in a cleaner and more sustainable way. So now you know a little bit about plasma, I'm going to tell you a little bit about myself and why I care about fusion. I'm a plasma physicist. I have a PhD from Imperial College London, where I worked on fusion energy. Now I work for private fusion company Tokamak Energy, and also with the Fusion Industry Association. But I'm also interested in the crossover between science and adventure. I've written a book about fusion and also a book about the Northern Lights. I've climbed Everest and written about the science that enables us to achieve it. I got interested in fusion after university. I studied physics as an undergraduate, and afterwards I was travelling around, working and wondering what to do with my life. I was already concerned about climate change and what we would do for energy in the future. This was reinforced when I went hiking and learned about glacial retreat. I was diving and seeing coral bleaching on the reefs. I was seeing science in the landscape. And then one day I read about fusion, this dream energy source, and I thought, if we could do this, it would be incredible. It would solve all our energy problems. So I went home and I started a PhD in fusion energy. That was 15 years ago now, and I'm still convinced that fusion is the best chance that we have for a sustainable future. But when I say I'm a plasma physicist, most people look at me blankly because most people don't know what plasma is. But what about you? Do you know what a plasma is? A plasma is an electrically charged gas, or it's the fourth state of matter. Now, you know about the states of matter. You know that we have solids, liquids, gases, and now we have plasma. Plasma is the most extreme state of matter in the universe. It only exists when there's enough energy in the system to strip atoms apart, like this. At such high temperatures, atoms break apart and become a charged gas called plasma, the fourth state of matter. Charged particles are affected by magnetic fields. They spin around field lines. And plasmas are all around us, so you're more familiar with plasmas than you think. The sun is a plasma. Lightning, flames, neon lights, all of these are plasmas that you're really quite familiar with. And this is the aurora, and here is a plasma in a tokamak. Fusion science. Fusion is a kind of nuclear energy. The cores of atoms come together, like building blocks. This is how all the atoms in the universe were made. In the sun, 4 hydrogen particles come together to make helium and release a huge amount of energy. The reason the fusion reaction releases energy is because if you weigh the 4 hydrogen atoms that you start with, and then weigh the helium that you get at the end, you'll find that the 4 hydrogens weigh more. So that means that during this reaction, everything's got a little bit lighter. They've lost some mass. And it was Einstein who said that energy and mass are equivalent. They can be transformed into one another. So you're probably familiar with Einstein's famous equation, E equals mc squared. This means that the energy that we get out is equal to the change in mass multiplied by the speed of light squared. And the speed of light is a really big number. It's 300,000 kilometers per second. So the speed of light squared is an even bigger number. And that means that all you need is a tiny, tiny change in mass, and you can release a huge amount of energy. So on Earth, we need to do things slightly differently to in the stars. We use slightly bigger building blocks, deuterium and tritium, which are types of heavy hydrogen. Deuterium and tritium come together and fuse. Protons and neutrons rearrange themselves, and they create helium and a neutron. Helium stays in the machine, and the neutron flies out, and we can extract that energy. And fusion requires very high temperatures, hundreds of millions of degrees. This is because the particles coming together are both positively charged, so they repel each other, like north poles of a magnet will repel. The only way to get them to fuse is to give them so much energy that they move around very, very fast, and they can slam into each other and fuse. So we need temperatures of hundreds of millions of degrees to do fusion. Different approaches and the tokamak. There are various ways that we can create the conditions required for fusion to occur, and some have been researched more than others. This next video tells you about some different approaches to fusion. In order to get fusion reactions going, you need to keep your fuel hot enough and dense enough, like the center of a star, and you need to keep it like that for long enough for fusion reactions to occur. This is encapsulated in something called the fusion triple product, NT tau E. Density, temperature, and the amount of time the energy is trapped are all multiplied together, and this needs to be bigger than a certain number to achieve fusion ignition. Tokamaks have shown good progress over time. But there is wiggle room. We could have higher density and lower temperature and a long time, like in the sun where hydrogen fuses to make helium. Or on Earth, if we fuse heavy hydrogen, we need higher temperatures, so can have lower density and a shorter time and still get to fusion conditions. This means that there are various different approaches when it comes to fusion and various different designs of fusion machine.
How many ways are there to achieve fusion that can give you net energy gain and have it be a possible way to produce electricity? And maybe half a dozen ways so far have achieved really truly fusion relevant conditions.
There are 2 main ways of confining or trapping hot fusion fuels. These are magnetic confinement and inertial confinement. Magnetic confinement uses magnetic fields to trap the hot fusion fuel. usually in a machine called a tokamak, or sometimes a stellarator. Inertial confinement uses a fuel pellet's own inertia, that is, its inability to move away fast enough to keep the fuel trapped and hot. Intense laser beams compress a tiny fuel pellet to obtain fusion conditions in the centre of the pellet. Others use shock waves. The most heavily researched approaches are tokamaks on the magnetic side and laser fusion on the inertial side.
A fusion plasma is a fusion plasma. They might have slightly different collisionalities and need slightly different theoretical models. But in the end, the foundational science is very much overlapping. Certainly, I worked myself most directly in magnetoinertial fusion, and we very much use the same theoretical constructs and modeling tools from both sides. So I do think there's a strong overlap in the science.
Historically, government funding was channeled into these two main approaches, which has resulted in some very large, impressive facilities like JET, ITER and NIF. The JET tokamak currently holds the world record for fusion power produced. Also, a lot of research has gone into understanding the fundamentals of fusion and plasma physics, as well as the specifics of these approaches. But there are other possible ways of achieving fusion. Other methods being investigated are magnetized target fusion, the field reverse configuration, the sustained spheromac, the dense plasma focus, the sheared flow stabilized Z-pinch, and more.
Having a lot of approaches is a good thing for fusion. It diversifies the risk because a lot of the concepts have different risk profiles. They have different reactor engineering requirements, and also pursuing multiple approaches actually it cross-fertilizes ideas at this point, which I think is useful.
From now on, I'm going to talk about tokamaks, because these are the machines that I work with. They're also the most advanced of fusion designs. A tokamak is simply a ring donut-shaped vessel with strong magnets that hold the plasma away from the walls. The word tokamak is actually a Russian acronym. It stands for Toroidalная камера магнитная катушка, which means toroidal chamber magnetic coils, which pretty much describes what a tokamak is. So we have one set of magnetic coils, the blue ones, that make a field that keeps the plasma going round in the ring. Then we have a current that we drive through the plasma in the same direction, the green arrow. This creates a field that pulls the plasma away from the walls. Then we can shape the plasma with the wide ring coils, the grey ones. These are the essential features of a tokamak, the inner workings, if you like. But of course, beyond that, we also have extra systems for heating the plasma or diagnostics for looking at the plasma. This brings us to JET. JET is currently the largest tokamak in the world, located in Oxfordshire, in England. This is a look inside the JET vessel. It's big. A man could easily stand up inside this machine. Now, on the left you see what the machine looks like empty, but on the right you can see what a plasma inside JET looks like. And one thing you might notice is that right in the centre of the machine where you expect the plasma to be, there's actually nothing there. Well, actually there is something there. The plasma is right there in the centre of the machine. You just can't see it. And you can't see it because it's so hot that the only light it's emitting is in the X-ray or the ultraviolet part of the spectrum. And we can't see that. All we can see is the cool stuff around the edges. So right in the centre you've got a plasma that's about 100 million degrees, and at the edges, by the walls where you can see the light, it's probably only a few thousand degrees. There's also another kind of tokamak design, which is called a spherical tokamak. This is just a squashed up version of the tokamak. It looks more like a cored apple than a ring donut. Spherical tokamaks have 4 key advantages over conventional tokamaks. 1, they are more efficient because the magnetic field is stronger closer to the centre of the ring. And in the squashed spherical design, the plasma sits closer to the centre. 2, they are better at keeping the plasma hotter for longer, something that physicists call the energy confinement time. 3, they suffer less from instabilities in the plasma, which could cause heat to leak out or disrupt operation. And so spherical tokamaks can potentially perform better. 4, They have an internal mechanism for producing a stabilizing current more effectively than conventional tokamaks. So they won't need to input so much energy to do this. This is a key point. It's a really important advantage of the spherical tokamak over the conventional tokamak when it comes to commercializing the technology and making a power plant. Because if you need to put in less energy to keep your plasma stable, you'll be able to get more out, which you can sell. Spherical tokamaks do have a disadvantage though, and that's that they have less space in the center because the design is more squashed up. This makes engineering more difficult. Is bigger better? Historically, progress towards fusion conditions in tokamaks was good, but the machines got very big. Let's have a look at why this was. It's to do with this equation. This equation says that the fusion power that we get out of a machine is related to the efficiency of the machine, something we call beta, the magnetic field strength, B, and the volume, or the size of the machine. So it's easy to see that for a fixed magnetic field, which is the expensive part of the machine, and a fixed efficiency, the only way, or the easiest way to increase fusion power is to increase the size of the machine. So after the success of the jet tokamak, the fusion community decided to build ITER. This picture shows ITER next to jet. ITER's about 2 to 3 times bigger than jet. Jet's almost 12 meters tall, whereas ITER is about 30 meters tall. ITER is currently under construction in the south of France. This slide gives a comparison of one of the big magnets in ITER. ITER has 18 of these toroidal field magnets, and each one of these magnets weighs as much as a fully loaded Boeing 747. ITER is a huge feat of engineering, but new technologies can change the picture. If we can find ways to increase the efficiency and the magnetic field strength, then we don't have to increase the size so much. Spherical tokamaks are more efficient than conventional tokamaks. They can achieve higher beta. So spherical tokamaks are a way to increase the beta parameter. High-temperature superconductors can make magnets that can make higher magnetic fields. So using high-temperature superconductors, or HTS magnets, is a way to increase B. This is a piece of HTS tape. It's very thin, but it can carry huge amounts of current without heating up. A superconductor is a special material that has zero electrical resistance. So when a current flows through it, the material doesn't heat up. You'll know that most materials heat up when electrical current flows through them. Some inventions even exploit this, like the toaster or the old-style light bulb. This property of superconductivity only comes into effect when the material is extremely cold. Most conventional superconductors, like those found in MRI scanners, operate at around 4 Kelvin, or minus 269 degrees C. A superconductor material also excludes all magnetic fields, so will push away from other magnets and can levitate. Superconductors are important materials for fusion, particularly for tokamaks or other machines that use magnets to confine the hot fusion fuel.
Fusion reactors rely on the production of enormous magnetic fields to confine the plasma in which the fusion reaction is happening. And the way we do that is with a giant electromagnet. And the only way that you can create the kind of strong magnetic fields required for plasma confinement is with superconductors.
Superconductors are important for fusion because they can run for hours on end without heating up, so they can be used to make the magnets that trap the fusion fuel. High-temperature superconductors, often referred to as HTS, are materials that can superconduct at higher temperatures than conventional superconductors, up to 80 Kelvin or minus 193 degrees C. This requires less energy to cool them. High-temperature superconductors are able to carry higher currents than conventional superconductors, which means that they can produce higher magnetic fields. They are also able to remain superconducting when they themselves are in a strong magnetic field. In this demo, you'll see how much current HTS tape can carry relative to copper. If we put the same amount of current that the HTS tape can take through a piece of copper the same size, well, see what happens. A few private companies are developing HTS technology, and it's seen as a game changer for fusion energy. So if we can increase the efficiency and the magnetic field strength using new technologies, we don't have to increase the volume so much. Also, there's nothing in the physics that says that fusion machines have to be big. The size of a fusion device depends on the approach adopted, on the engineering and the technology. And as we have seen, these vary greatly. This gives me a lot of hope because technologies always change. So just because we have to make big machines now doesn't mean that they will always have to be this size. Tokamak Energy is working on a modular solution for fusion, meaning that we'll make smaller machines that can be grouped together to make larger power plants. Smaller machines mean easier commercialization. They open up the possibility of factory production and allow us to reduce costs. But a modular solution also gives more flexibility in the way a power plant is operated, because you wouldn't need to have them all on at the same time. So you could change the amount of energy that's being produced. And also, it's easier if repairs need to be made, because one machine can be on downtime, but you can still make energy using the rest of the machines. Tokamak Energy is working on modules that may be like 100 to 150 megawatts, and several of these could be grouped together to make a bigger gigawatt scale power station. Or individual modules could be used where requirements are lower. We still don't know exactly what size these modules will be. They could be jet-sized, but it depends a lot on the engineering and material science. Tokamak Energy. Tokamak Energy wants to accelerate the development of fusion power, and it will do this by combining two emerging technologies: the more efficient spherical tokamak shape and high temperature superconductors, or HTS, which are able to make higher magnetic fields. Tokamak Energy was founded in 2009 as a spin-out from the Cullum Centre for Fusion Energy. To date, they've raised over £120 million. They've successfully built and tested 3 prototype tokamak devices, and now they have a team of over 100, including world-leading physicists and engineers. They also have over 50 separate patent families. In the early days, Tokamak Energy was building up its capabilities, and it built a small tokamak called ST25. This is a picture of ST25. It's kind of about the sort of size that you could almost put your arms around it like this. After that, they built a similarly sized tokamak, but with HTS magnets. So this is a picture of ST25 HTS. And this machine held a plasma inside it for over 29 hours. And this was a world record because it was using these new high temperature superconducting magnets. So it was a demonstration of that early HTS technology. The next step was to build a larger tokamak. This is an engineering drawing of ST40 with one of our founders, Alan Sykes. The aim of ST40 is to reach fusion temperatures, 100 million degrees, but also to see how the plasma behaves in this squashed up high field configuration. In this next video clip, you'll see how ST40 comes together. So those are all the important components of ST40. Here's how they'll be assembled. The inner vacuum chamber with the merging compression and diverter coils. The center column and solenoid that slots down the middle. Next come the return limbs and their supports, followed by the outer vacuum chamber and the remaining vertical field coils. This will be ST40, the world's first compact high field tokamak. Here are some pictures of ST40 under construction. So this is a picture of the inner vacuum vessel. And this is the inner vacuum vessel with the copper magnetic coils around it. This is the outer vacuum vessel. So this is the outer vacuum vessel just being put onto the machine. And then this is another view of the tokamak with the one of the big colloidal field coils going on. And this is the machine when it was first constructed and ready to operate. This is a picture of the inside of the machine. You can see the plasma forming around the inside coils. It just needs to be pushed into the center. In 2018, we achieved a major milestone. We reached 15 million degree temperatures in ST40. That's hotter than the center of the sun. We also moved into a new, much larger facility because the team was growing quickly. This video shows the construction of ST40 in its new home. This is a picture of the control room. This is a video of a plasma in ST40. In 2019 and 2020, we have been upgrading ST40 with the aim of achieving temperatures of 100 million degrees. This will put us well on the way to getting past energy break-even and building a demonstration power plant. As well as the aim to achieve fusion temperatures in ST40, it's also a world-class tokamak doing fusion research. ST40 is the world's highest field spherical tokamak, designed for magnetic fields of 3 Tesla. In ST40, we tested a way of starting up the machine using a technique called merging compression. This is a way of starting up the plasma without using a central solenoid. Instead, you break the plasma down around 2 coils inside the vessel, and then use magnetic fields to push these 2 blobs together, as you can see in the picture, to make a stable plasma ring. When these 2 blobs come together, magnetic fields break and reconnect and release huge amounts of energy. So this method of startup is also a way of heating the plasma. In 2019, Tokamak Energy made an announcement of the results of their HTS development program. They achieved a peak field on the coil of 24.4 Tesla, which was a world record, which is the field required for a tokamak. These magnets are extremely robust, reliable, and easy to manufacture. And our HTS program is well ahead of schedule. When will we have fusion? This is the hardest question to answer. It depends on money, people, politics. It's not just up to the scientists. I can give some estimates, but it's science, it's an exploration. It's never been done before. That makes it exciting, but we don't know exactly what's going to happen. These are Tokamak Energy's steps to fusion. First, we demonstrated initial capabilities and the necessary technology in ST25 with HTS magnets. Next, the ST40 and HTS development tracks come together into our next device, STF1, which aims to be operational by the middle of the decade. This will achieve fusion energy and get past energy break-even. After that, we'll build STE1 for electricity production. We're aiming to demonstrate electricity on the grid by 2030, ready for commercial rollout throughout the 2030s. Also by 2030, hopefully ITER will be operating, so we'll be getting results from there. ITER is a huge feat of engineering and it's currently under construction in the south of France. And what about the other startups? Maybe by 2030, one of these will have achieved fusion. These are some of the members of the Fusion Industry Association, which is growing all the time. So what can you do to support fusion? You can become part of a fusion movement. You can tell people about fusion, help raise awareness. You can educate young people who are the ones who will be living with fusion energy. You can follow the Fusion Industry Association and other fusion companies for updates on progress. And you can demand change from government to get away from fossil fuels. So in summary, fusion is the energy of the stars. It is needed on Earth for clean, reliable baseload power. The science is mature. New technologies are changing possibilities. Climate urgency is rising. Private investment is moving the fusion field towards commercialization. Tokamaks are the best understood of all fusion approaches. Tokamak Energy is bringing in new technology to enable compact, modular, economical fusion power. Tokamak Energy and other startups hope to demonstrate commercial feasibility by 2030. Now is a crucial time as we move into the era of commercial fusion energy. We need dedication, investment, smart people, and public support. I hope we have yours. Thank you.
Melanie, thank you so much for that. I've got a quick question as a complete fusion novice. Do you think that there could ever be a time when we could get as enthusiastic about fusion technology as we got about the space race and get entire nations behind it, or do you think it's just not glamorous enough yet? So what we need is a good-looking young president to announce that it's going to be his mission for the next election. But in this current electoral cycle, I don't think that's about to happen. We've got some questions here from St Mungo's Academy, and I think we've actually got film of our young scientists actually putting the questions to you.
Things will need to change in order to use fusion energy. Who's opening their wallets?
We need a leader. When, how and who will this be taken forward by?
The EU is doing this. What about us? How long is this going to take?
So what's the outcome?
As soon as they're finished, I'll... So, just in case you didn't catch the questions, Melanie, I'm a little bit of a Glaswegian whisperer at the moment, so I'm kind of translating. So, these kids were asking the things that we need to change in order to use fusion energy. So, this is an excellent question here from Pamela, Bryony, Mark and Ren. Who's opening their wallet? Who's paying for this?
That is a very good question. Historically, fusion has been funded by governments because when the research was, was very exploratory and new, it was funded by governments and public labs. What's interesting about the last 10 to 15 years is that we've seen a really big increase in the amount of private investment going into fusion. So that means private companies like Tokamak Energy and others being funded by either wealthy individuals or increasingly, which is also interesting, now some strategic investors like Legal and General, some oil companies, sovereign wealth funds, those kind of things. And so this is showing us that fusion is tipping over to becoming a commercial reality because of that change. So we still need a lot more investment into fusion, of course, to actually take it from the science basis to like a real economic power plant. And I think that's going to need a mixture of government and private support. So we need to have partnerships in place. The government needs to create the right climate, if you like, for private investment and for private companies to thrive. So things like partnerships with public labs, between the private companies and the public labs are very useful. And also things like certainty around like regulation and licensing needs to come from government as well to enable more private investment to come into the space. But so that's a really good question. And yes, the funding is changing. It's moving much more from government into the private sector, and that is really exciting for fusion.
Well, I think St Mungo's Academy were like one step ahead of you on that one, because their next question is, you're talking about funding and partnerships, but who's going to be taking this forward? Who's the leader in this?
That's also an interesting question, and I think so because there are various different private companies working towards it. There is, you could say, like something of a race going on in that companies want to be first to commercialize the technology. But I think that, as I mentioned before, governments need to take leadership in creating the right climate for this. So taking leads on sustainability and climate targets, which we're seeing more of now anyway, taking leads on regulation and licensing so that the private companies can thrive. Those kind of things are really important. So that's the kind of leadership we need. I don't think it's going to be, one lab or one country saying, okay, we're going to do fusion. It's going to be a mixture of partnerships. It's going to be a mixture of the private companies and the public sector. So yeah, we need strong leadership from government to say we want this to happen, and let's work together to make it happen.
I understand that the EU is probably doing work on this, and that kind of leaves us with an awkward question, but we have to ask it. Where does that leave us?
Well, actually, there's a lot of work going on globally in fusion. So the machine ITER that's being built in the south of France, that is a worldwide collaboration. It's being hosted by the EU, of course, it's being built in France, and the UK is one of the contributors to that as part of the EU. And I think, and it will still be part of that in some form after Brexit. But also part of ITER are like the Americans, India, China. There are various partners in this. But also, as I said, there's now private companies coming in, and it's the private companies that are going to drive fusion towards commercialization. And there are private companies springing up all over the world. The UK, the US, and Canada are arguably the leaders in this. So the UK is very much involved in fusion. Like, historically, it's very strong on fusion research. They host the JET Tokamak, which is currently the biggest tokamak in the world, but more importantly, the best performing in the world. So the UK has a lot of expertise in fusion energy, and now with private startups like Tokamak Energy, and there's another called First Light Fusion, the UK is still like very much in the game, if you like, when fusion is concerned. And so I think the UK has a lot to offer globally in terms of fusion development.
Okay, so the question from St Mungo's Academy is this one's particularly poignant in a way, bearing in mind the age of the children, from Pamela and Brian and Mark and Ren. How long is this going to take, Melanie?
Well, that's a very, very big question, and one that I can't answer completely. I think I mentioned in the video. It's science. It's an exploration. We don't know exactly what's going to happen. That makes it really exciting, but it also makes it difficult to make predictions. And also, it's not just down to us. As I mentioned before, it's down to the government and creating the regulation and the licensing framework, and it's down to the amount of money that we have, and it's also down to the kids themselves, the smart people coming up into the field and helping to push this forward. You know, all of those things contribute. So ideally, a lot of the kind of leading fusion companies want to demonstrate the commercial viability of fusion this decade. So that means they need to get more energy out of the reaction than they put in, preferably by the middle of this decade. And then they need to build a machine that generates electricity, preferably by 2030 or around 2030. And that will mean that we can then roll out fusion in the 2030s commercially. Because, of course, technologies take a while to build up. It's like a snowball. You know, you start with one, and then a few more, and then a few more, and a few more. So it's not like it's suddenly going to turn on and we're all using fusion. It's going to go from the first power station, and it's going to build up. So we need like help to scale that up, and this is where like the governments come in, and the energy companies come in, and the funders come in. So this is what's going to drive fusion. So if we have enough funding, the private companies have enough funding, and we have enough partnerships with public labs to do some important science over the next decade, then we've got a really good chance of rolling out fusion in the 2030s. But all of these things need to come together. The funding and the research and the people, like all of these things need to come together. So let's make it happen.
Well, let's make it happen. But the final question that they have for you from St Mungo's Academy, and you gave us some timeline there, within a decade. But what is going to be the outcome? So you gave us a bit of a timeline there. Could you speculate beyond that first decade?
So what's the outcome? The outcome would be energy, clean energy, globally. And fusion is not just capable of making electricity. Fusion can help us decarbonize areas that are difficult to decarbonize. For example, it could be used to make hydrogen or synthetic fuels. It could be used to produce industrial scale heat, which can be used for industries like cement making or steel making. All of these areas are difficult to decarbonize. So fusion could have a big impact by not just producing electricity, but also by decarbonizing some of these difficult industries. So that will be the outcome. It will mean that we have clean, safe, sustainable, and abundant energy like forever, essentially, because you're not going to run out of fuels, because fusion produces such a lot of energy from only a small amount of fuel, and crucially from a small amount of space as well, because renewables are doing really well and they're scaling up really, really well. But they do take up a lot of space, and they're better in some areas than in others. And also they produce electricity, and sometimes we need things besides electricity. So this is where fusion can help. I think that it can really complement renewables so that we can live in a future where we have sustainable energy, but abundant energy, so that people can develop and grow, and we can improve lifestyles in areas of the world where they don't have significant energy at the moment. So that's the key outcome, like global, clean, sustainable energy.
That's excellent. So I've got one question here that's come in, but can I just say to St Mungo's Academy, to Pamela Bryan, Mark and Wren, great questions, but you did hear what Melanie said. It's also down to you. Get that homework done, and then we expect you to be the scientists of the future, and you can solve all this problem for us as well. But we have a question that's come in here, which is, everything's been very optimistic so far and very, very gung-ho, dare I say, but there's a question here, and it's from Fiona. Are there any dangers involved in fusion?
So dangers involved in fusion, not significant dangers. There's no risk of meltdown of the machines or of the reaction. It's a reaction that powers the stars, as I mentioned, but that makes it very, very hard to do. And the conditions have to be perfect in order for the reaction to happen. This makes it inherently very safe, because if the conditions aren't perfect, then everything just cools and stops. Even if the plasma, if you lose control of it in those magnets and it hits the wall, then it's not great for the wall, admittedly, but it's not dangerous. Everything just cools and it stops. You're left with a load of gas in your machine and you have to start up again. So it's inherently very safe. However, it is a nuclear reaction, and it does produce neutrons, and neutrons themselves, they have a lot of energy, and when they fly out of the machine, they go through the walls of the machine, and they can actually knock atoms out of position in the walls of the machine. And this can mean that it changes it slightly. It can transmutate materials, and that means that it can make the machine itself slightly radioactive over its lifetime. So although fusion doesn't produce any long-lived radioactive waste, the machine over time will become radioactive, and that means that it will just need to be decommissioned and disposed of properly and carefully at the end of its lifetime, as you would do with any other big plant. And this radioactivity is not long-lived radioactivity. It would be short-lived, probably able to be like recycled and safe after like 50 years or so. It's like low level. And people are working to reduce that radioactivity of the machine. And of course, it also uses a radioactive fuel, which is tritium. So this has a very short half-life. It's about 12 years or so. So it doesn't stay around for a long time. And we use tritium for lots of other things. But it does mean that you don't want to have lots of tritium on your site. You have to think about handling the tritium carefully as well. So that's something that is will be considered in the regulations that the government put into place. So it just requires careful handling. So there are certain things that you have to be aware of for fusion, but people generally say that the plant would be maybe at the same kind of danger as any industrial site, for example. And the regulatory framework, they're being investigated at the moment. We don't know exactly what they will be, but it's hoped that they won't be as stringent as nuclear fission, for example, because it's a very different technology. It could possibly be regulated in the same way that medical isotopes or radionuclides are regulated. But that is too early to say that yet, because governments are still putting the regulations in place. So, like any technology, it does have its issues, but all technologies do, and it's a matter of how we handle them and how we assess the risk. I think that's important.
Well, it certainly sounds safer than the nuclear options currently available. Melanie, we're going to let you go now to rest your voice, because you have another event, which I think spaces are still available for on Zoom. Yeah, you can go down to the bottom of the screen. You can register for that event if you look at the bottom of the screen. So Melanie's going to go and rest her voice so she can carry out that event, which starts at 5. Is that right, Maggie? Excellent. However, that's us for today from here, from The Big Bounce. Don't forget, there's a feedback at the bottom of the screen. If you fill it in, you can enter the free prize draw. The prize for which, I'm not making this up, is, if you win the prize, the free prize draw, it is a Lego version of the Barrowlands. I should point out it's a model version, it's not a full-size version, because you just wouldn't get planning permission for that if you're in a bungalow or something. But if you go and do the feedback, you'll be able to get into that free prize draw. So that's us today from The Big Bounce. Join us tomorrow. We've got great events tomorrow, Power Up, all sorts of exciting stuff going on, and the Cabaret of Dangerous Ideas. I've been Susan Morrison. You've been great to talk to. Join us again tomorrow and get the questions coming in, and join Melanie again at 5 o'clock. Thank you very much for joining us. Good night, everyone. Bye-bye.